right, everyone, welcome once again to our set theory seminar, and thank you for paying attention to my email and seeing the new Zoom link. It's absolutely great to have Gabe Goldberg here again. I really enjoy his talks, and he will be speaking today on cardinal preserving embeddings and strong compactness. All right, Gabe, take it away.
Thanks. Okay, so the motivation for this talk comes from the CUNY inconsistency theorem. So if you don't remember, this says that there is no elementary embedding from the universe of sets V to itself, except for the identity. The point of this theorem is that it places an upper bound on the kinds of large cardinal axioms that are consistent with ZFC set theory. Normally, or the strong large cardinal axioms are typically formulated in terms of elementary embeddings from the universe of sets into some inner model, and they get stronger and stronger as the inner model gets closer and closer to V, but it can't get all the way. Okay, and there are constraints, somewhat stronger constraints than what I wrote down, but let me not talk about them right now. So one can also drop the axiom of choice, and then it seems that embeddings of this form, so non-trivial elementary embeddings from V to itself, are consistent. At least there's some kind of interesting structure that comes from them that's been developed recently. And it also seems that these axioms are stronger. So these axioms that don't involve the axiom of choice are stronger in terms of consistency strength than any known large cardinal axioms. So consistent with ZFC, which poses some kind of philosophical problem. If the point of set theory is to be our theory that can interpret all other mathematical theories, so we have our large cardinals, and they're supposed to show us the consistency of whatever combinatorial statements we want, but now we have these very strong theories consistent with ZF that seem not to be interpretable in any natural extension of ZFC. Okay, so the question is, is there some way to extend the large cardinal hierarchy in ZFC to obtain axioms at this level? I mean, the hope, I think, is that large cardinal axioms should be co-final in the consistency strengths. Anything that's consistent should be proved consistent from a large cardinal axiom. So we could calibrate the consistency strength of any theory in terms of large cardinals, but it seems like the CUNY inconsistency theorem and the existence of this hierarchy beyond the axiom of choice is giving a counterexample to that. So the question is it really a counterexample? Okay, and this talk is about one way to try to find large cardinal axioms at this level. Mostly it's negative answers to these questions. But okay, so Caicedo posed following questions. So can there be a non-trivial elementary embedding first from the universe of sets into a cardinal correct inner model? So this just means that the cardinals of M are exactly the cardinals of V. So in other words, M correctly computes successor cardinals. That's all this amounts to. And then his second question was, can there be a non-trivial elementary embedding from a cardinal correct inner model? Into the universe of sets. Okay, so question 2 is kind of a stranger thing. At least the simplest story of large cardinal axioms is that they involve elementary embeddings of the universe into smaller models, not smaller models into the universe of sets. But actually, large cardinal axioms do give us something like embeddings from inner models into the universe of sets. So these are related to Janssen cardinals, these embeddings that go the other way. So we'll talk about that later. Okay, so I think that Caicedo's motivation here was just, well, this is one way to weaken the hypothesis in the CUNY inconsistency theorem to make it not at all obvious that you can get a contradiction even in ZFC. And these principles look extremely strong. They imply forms of strong compactness that look like they're beyond or at the level of the CUNY inconsistency. So we have this kind of global resemblance between V and the models it's embedding into or that are embedding into it. Okay, so maybe one trivial observation here is that if you have a cardinal correct inner model M, or just any inner model M, there can't be both an elementary embedding from V to M and an elementary embedding from M to V. That's just by the CUNY inconsistency theorem, because you could compose them and get a non-trivial elementary embedding from V to V. I don't know, it's kind of funny. It's totally irrelevant to the rest of the talk. Oh, and by the way, I should say these kinds of embeddings will be called cardinal preserving embeddings. So we'll either talk about cardinal preserving embeddings from V to M, that's like question 1, and cardinal preserving embeddings from M to V. Okay, and this terminology, don't get confused. It doesn't just mean that if you take a cardinal in one of the models, then it's mapped to a cardinal in the other model, or even just if you take a cardinal, it's mapped to a cardinal. That's, I think, what cardinal preserving sounds like it would mean. It just means that the models involved are cardinal correct. So the two theorems I'll discuss basically, well, they verify Caicedo's, I think he even makes this conjecture in the paper where he asks these questions. The conjecture that these axioms are actually false. So the first theorem has a large cardinal hypothesis. So it says if there's a proper class of strongly compact cardinals, then there's no cardinal preserving embedding from V into an inner model. So if you have any cardinal correct inner model, I mean, I guess except for the identity. Always have to say that. So here the idea is that at least, even if it doesn't rule out cardinal preserving embeddings from V to M outright in ZFC, at least we show that this is not a way to extend the large cardinal hierarchy, because we show that it is incompatible with other, I guess, more plausible large cardinal axioms. So this is showing that cardinal preserving embeddings from V to M aren't, I guess, a genuine large cardinal axiom. I don't know exactly how to put it, but I think that in some way this answers the philosophical question about cardinal preserving embeddings from V to M. about as well as an answer in ZFC would. So still, as I said in the abstract, it's open whether cardinal preserving embeddings from B to M are consistent. And if there's time at the end of this talk, I'll discuss that. Okay, and then the second theorem, which is joint with a graduate student, Sebastiano Te, who was visiting Berkeley for the past few months, is about the other question. And it's actually, well, it wasn't in the abstract because the final result is only proved on Wednesday. But the theorem is there are no cardinal preserving embeddings. From M to B. So this answers the second of Caicedo's questions, just in ZFC. And you know, having answered in ZFC, I see how much better it feels to answer something in ZFC than to answer it from a proper class of strongly compact cardinals. But still, I do think that theorem one philosophically says just as much. Okay, so I'm going to first discuss what goes into theorem one. So this is sort of, it uses some techniques developed by Wooden involving weak extender models for supercompact cardinals, adapting these to strongly compact cardinals. Some ideas due to Silver about indecomposable ultrafilters. And then I'll talk about what goes into theorem two. So this is a matter of singular cardinal combinatorics. So ideas about square, about Janssen cardinals that are due to Scheller, and some ideas about good scales and strongly compact cardinals that are due to Bagheria and Magador. So you'll see. So this is singular cardinal combinatorics. And this is weak extender models. Okay. So section one. So the first thing we should look at is what kind of cardinal preservation is possible, at least assuming strong large cardinal axioms. So the axiom I2 states that there is an elementary embedding J from B to M. Okay, so it's parameterized by this lambda with critical point strictly below lambda, such that, okay, J fixes lambda, and V lambda is subset of M. Now, the point here is that it's a rank into rank axiom. It's an axiom just below the CUNY inconsistency theorem. So let me describe how that works out. So assuming this axiom is true, then letting kappa be the critical point of J, kappa is n huge for every n. Okay, so, and this is basically witnessed by this elementary embedding J. Whereas the CUNY inconsistency says something like omega hugeness is impossible. So in other words, this means that, that lambda is actually forced to just be the supremum of the iterates of J on kappa. So this is the cardinal that really comes up in Kunin's proof of the CUNY inconsistency theorem. And Kunin shows that the amount of strength this embedding has cannot be increased by 1. In other words, V lambda plus 1 is not contained in N. So this is the kind of structure of this kind of embedding that you get from Kunin's argument. Okay, cardinal preservation. So what does this have to do with cardinal preserving embeddings? Well, because V lambda is contained in M, we know that the cardinals of M up to lambda are the same as the cardinals of V up to lambda. Okay, so that's one thing, but actually we get a little bit more. So if you look at the picture, which I'll draw so you can look at it, we have lambda, and lambda is actually a fixed point of this embedding. That's sort of, well, I guess that's part of the assumption here. So remember, this Kunin inconsistency fact showed that lambda is the result of just iterating J on starting at the critical point. So it's just the supremum of those ordinals. Okay, but lambda plus must also be fixed because, well, if lambda is fixed and lambda plus can't get pushed down because elementary embeddings always are order preserving, so they move ordinals up. But it can't get moved strictly above lambda plus because lambda plus gets mapped to lambda plus of M, and lambda plus of M can only be less than or equal to the true lambda plus. It's sort of a pi 1 property to be cardinal. Okay, I hope you know about that. Okay, so, and lambda double plus, for the same reason, has to be fixed. And moreover, lambda plus alpha has to be fixed for any alpha less than kappa, the critical point. Then lambda plus alpha plus kappa is shot up. But okay, general theory of elementary embedding stuff tells you, okay, that lambda plus kappa plus 1 is actually correctly computed by M. Okay, so this tells us that M correctly computes all the cardinals up to lambda plus kappa plus 1, right? The fact that lambda plus was fixed by this embedding tells us that lambda plus of M is just lambda plus. Similarly, the fact that all these things are fixed tells us that they're actually correctly computed by M. And then finally, I had this sort of hand-wavy thing where I said that the general theory of elementary embeddings tells you that lambda plus kappa plus 1 is actually correctly computed as well. Okay, and the natural way of obtaining these kinds of embeddings is by taking an ultrapower by an extender. I'm not going to say that much about that, but the cardinal preservation can fail at lambda plus kappa plus 2. So this can be, and in all natural examples will be, strictly less than lambda plus kappa plus 2. I guess maybe I'm assuming the GCH here for that calculation, but at least this model M will not be, in the natural examples, cardinal correct all the way up to lambda plus J of kappa. So the most cardinal preservation that we can get from large cardinal axioms is all the way up to lambda plus kappa plus 1. And this tells us that if we're trying to refute a cardinal preserving embedding from V to M, the place we should look is above lambda plus kappa plus 1, unless, you know, we get ambitious and we decide we're going to refute large cardinal axioms at the level of I2 of lambda, but I'm not that ambitious. Okay. So let me tell you how I got interested in these questions. They were sort of test questions for the theory I worked on in my dissertation. So this involves a set theoretic principle I introduced called the Ultrapower Axiom. So what I said on the slide is that it axiomatizes part of the large cardinal structure of the canonical models built in inner model theory. So for example, the inner model L of U. So it's trying to axiomatize basically the comparison lemma from inner model theory, but that involves, at least the level it's studied today, involves fine structure theory. And so to get an abstract principle, you can only state certain fragment of the comparison lemma. So the ultrapower axiom gives you this fragment basically for ultrapowers, which turns out you can state in a pretty convenient way. What it says is take any two countably complete ultrafilters, U0 and U1. So for all U0 and U1 countably complete ultrafilters, there exist W0 and W1. Okay, so what are these objects? They're kind of countably complete ultrafilters internal to these models. I guess I should write these models are. It's supposed to be the ultrapowers. So V by U0, ultrapower V by U1. So inside of the ultrapower of V by U0, you can find what looks relative to that inner model like a countably complete ultrafilter W0. Inside this, a countably complete ultrafilter W1, such that the ultrapowers you get are isomorphic, or for set theoretic purposes equal, because their transitive collapses are equal. Okay, so that's what the ultrapower axiom says. The motivation is, for example, if you've seen L of U, take any two L of U like models, you can iterate their measures and make the two models the same. Okay, it turns out that if you take any two ultrapowers of L of U by its models, those are two L of U like models, and you can iterate those to make them the same. And actually, if you take a hull, you'll see that all you needed to do is take two ultrapowers to make them the same. So the ultrapower axiom actually holds in all of the canonical models of set theory, and it holds for very general reasons. So it's like a one-line proof given the comparison lemma that the ultrapower axiom is true. And so the hope is that the ultrapower axiom will hold in canonical models that we haven't built yet. And this way we can study large cardinal axioms beyond the current inner models, but in the context of the ultrapower axiom, to try to get a sense of what the canonical models for those large cardinal axioms will look like. Okay, so one thing you can prove from the ultrapower axiom is that there are no cardinal preserving embeddings from the universe into an inner model, so E to M. And the way this works is by connecting cardinal preserving embeddings to the CUNY inconsistency theorem. So for context, one thing that UA, the ultrapower axiom, is able to do is connect large cardinal axioms, especially at the level of strong compactness and super compactness, that in ZFC are not equivalent, but that seem to be equiconsistent. So the big open question, one big open question in large cardinals is the equiconsistency of super compactness and strong compactness. And the ultrapower axiom just shows that the least strongly compact cardinal is super compact. So we can view this no non-trivial cardinal preserving embeddings theorem as just another example of UA correctly calibrating some kind of weak or strong compact like large cardinal axiom with its super compact variant that's equiconsistent, hopefully. So let me make that precise. So this theorem on cardinal preserving embeddings can be made into something more substantive. So suppose J goes from V into M, and lambda is a cardinal above the critical point J, such that, well, J of lambda is equal to lambda. The cardinals of M up to lambda are equal to the cardinals of V up to lambda. Okay, and I need one more hypothesis here to rule out that we're in this weird case. I could be looking at something, I want to say that then we're in the case of I2. So that V lambda is contained in M. But it could be that we're looking at these cardinals above lambda, that where we already have cardinal preservation, like this, what if we're looking at lambda plus alpha instead? Then V lambda plus alpha is not contained in M. So what I'm going to say instead, well, my final hypothesis is that lambda is an Aleph fixed point, so it's equal to Aleph lambda. Okay, so that rules out all of these cardinals in that interval between lambda and lambda plus kappa. So it specifies what lambda should be. Okay, then V lambda is contained in M. Okay, so the ultrapower axiom shows you that if you have a cardinal preserving embedding at an Aleph fixed point, up to an Aleph fixed point, then it's just an I2 embedding. That's the only way these things can come about. And so it's impossible to have a fully cardinal preserving embedding because there would be a proper class of lambdas such that J of lambda is equal to lambda, and lambda is an Aleph fixed point. That's kind of how elementary embeddings from V into an inner model work. You can always find an omega closed class of fixed points. So you can always find a closed class of fixed points that are Aleph fixed points as well. And then you would get that V lambda is contained in M for arbitrarily large lambda. So M would be equal to V. And then you would have a non-trivial embedding from V to V. So the way UA rules out cardinal preserving embeddings is by showing that a cardinal preserving embedding is the same thing as an embedding from V to V, which is ruled out by the CUNY consistency theorem. All right, so this is kind of, I don't know, it's exactly the way you would hope to rule out cardinal preserving embeddings in the canonical model context. And it argues already against cardinal preserving embeddings as a large cardinal principle in CFC. So, okay. How are we going to sort of transfer these ideas to rule out cardinal preserving embeddings from large cardinal axioms? Well, the proof, if you look more closely at this proof, you can rule out any embedding that's cardinal preserving, beyond lambda plus kappa plus 1, and that's by looking at a specific ultrafilter. So let me define this ultrafilter and what the bad properties of it are. And then we'll try to rule that out using strong compactness instead of using the ultrapower axiom. So an ultrafilter U is kappa gamma indecomposable. So this is a weakening of gamma completeness. It's kappa gamma indecomposable if for any A, a collection of subsets of U of size less than gamma, a collection of elements of U of size less than gamma, if the intersection of A is not itself an element of U, then there is already some A0 contained in A of size less than kappa, such that the intersection of A0 is not mu. So this is saying that any failure of gamma completeness for U reduces to a failure of kappa completeness for U. So, for example, if your ultrafilter is kappa complete and it's kappa gamma decomposable, then it must be gamma complete, just essentially by definition. So the notion of an indecomposable ultrafilter goes back to the 60s and 70s, studied by people like Kiesler and Pricry. And let's see, the notion they typically studied was that of an Aleph 1 gamma indecomposable ultrafilter. So this is interesting in the context of ultrafilters that aren't Aleph 1 complete. It's a little afield of what we're looking at, since we're always looking at, in this talk, well, typically up to this point, I've been looking at well-founded models. But it makes sense. So it's saying that the failure of completeness reduces to the countable incompleteness of the ultrafilter. Okay, but it's more general. This concept is more general and more relevant for us. Okay, but basically, this isn't totally accurate, but it's close. If you don't like to think about ultrafilter combinatorics, you prefer to think about ultrapowers. This is basically, but not quite, saying that the ultrapower embedding is continuous at all regular cardinals in the interval kappa gamma. Okay, so that is a consequence of kappa gamma indecomposability. It's not a, let's see, maybe I should say kappa. Let's put kappa gamma. That's a consequence of indecomposability, but it's not quite. Indecomposability is a little stronger. It really says that the ultrafilter can't Rudin-Kiesler project onto any uniform ultrafilters in that interval. Okay. So suppose you have a cardinal preserving embedding E into M. And I'm going to show you how to get some indecomposable ultrafilters from it. So they're just derived ultrafilters. So you take kappa, the critical point, and then you take any fixed point above kappa, and I'll define an indecomposable ultrafilter on lambda plus kappa. So U alpha is just the set of all A contained in lambda plus kappa, such that alpha is in J of A. Okay, so pretty familiar from the theory of measurable cardinals. This is how you get a measure from an embedding. Okay, so these ultrafilters, because J, as we saw before, has to fix every cardinal between lambda and lambda plus kappa, these ultrafilters will be lambda plus kappa indecomposable. By this, basically, claim up here, which is not quite true, but actually in our context, it is true. Basically, because I keep saying basically, but because the all these ultrafilters are also kappa. Okay, and it's also true that for some alpha in lambda plus kappa, lambda plus J of kappa, U alpha is a uniform ultrafilter. which just means every set in U alpha has cardinality lambda plus kappa. So this won't be true for every alpha in the interval. For example, if you use lambda plus kappa, if alpha is equal to lambda plus kappa, the ultrafilter U alpha will not be uniform. It will concentrate on a set of size kappa. So for a singular cardinal like lambda plus kappa, there can be ultrafilters that concentrate only on unbounded subsets, but are not uniform because they concentrate on a small set. But you can find an alpha, and I'm not going to tell you exactly how, but it has to do with the fact that you're cardinal preserving, such that U alpha is uniform. I mean, you can define these U alphas even if you're not looking at a cardinal preserving embedding, and they're kind of pathological objects. In the context of the ultrapower axiom, you can just rule out the existence of something like this. So talk about that. So back in the 70s, when people were looking at indecomposable ultrafilters, Silver posed the following question. Suppose that gamma is inaccessible and carries a uniform Aleph-1 gamma indecomposable ultrafilter. Is gamma measurable? So the motivation for this question is that Silver had this factorization theorem for Aleph-1 gamma whatever indecomposable ultrafilters. So factoring the ultrapower embedding, what he could do is find an ultrafilter D on omega so that if you take the ultrapower of V by D, it resembles the ultrapower of V by U in a very strong sense. K, the factor embedding that you'll get back from the ultrapower of V by D into the ultrapower of V by U, well, I want to say it has critical point. That's a very large critical point. But let's just say that K restricted to JD of alpha is equal to the identity for alpha less than gamma. Okay, so I don't want to talk about the critical point because we're in the context of ill-founded models, and the critical point is supposed to be the least ordinal that something moves, but K is not necessarily definable over alt VD, so there may not be a least ordinal that moves. Actually, I think in this case there is one, but let's not worry too much about it. Okay, so if K is actually definable over alt VD, then we would get that its critical point is measurable. Okay, and this would show in the context where gamma is inaccessible, that gamma would have to be measurable. But it's not clear that K has to be definable. So anyway, this is the reason I think that Silver asked this question, that it seemed maybe even slightly plausible, although I think he thought the answer would be no. And in fact, the answer is no. It is consistent, at least, that Silver's question has a negative answer. Actually, in the inner models, in the canonical models, like the core model with many measurable cardinals, the only places you'll see these indecomposable ultrafilters on on inaccessible cardinals, it is only on the measurable cardinals. Okay, so Silver's question canonically has a positive answer. And also under UA, the version for Aleph-1 complete ultrafilters has a positive answer. Now, you don't want to ask too trivial of a question. If you ask about an Aleph-1 complete, Aleph-1 gamma indecomposable uniform ultrafilter on gamma, well, gamma is going to be measurable because any Aleph-1 complete, Aleph-1 gamma indecomposable ultrafilter, as I said before, is just gamma complete. Okay, so assuming you followed me saying that. So you have to ask something a bit less easy than that. You want to say things that aren't just trivial. So under UA, we have that if gamma is inaccessible and gamma carries an Aleph-1 complete, countably complete ultrafilter, let's say uniform ultrafilter, that is kappa gamma indecomposable for some kappa less than gamma. So meaning eventually it's continuous at all regular cardinals below gamma. So it's continuous at all sufficiently large regular cardinals below gamma. Then gamma is measured. Okay, so UA really only helps you with countably complete ultrafilters, just sort of by the nature of UA. It's not, there are some minor things you can do for incomplete ultrafilters, but here it's not really much use as far as I can see. So you want to go into the Aleph-1 complete context, but generalize the question so that there's something substantive to say. Okay, and this is what you can say. So Silver's theorem, the Aleph-1 complete version has a positive answer under UA. And the basic idea is, well, we look at Silver's diagram here and show that K is definable over all of VD. The way you do that is by comparing these two ultrapowers, using the Ultrapower Axiom and showing that the diagram commutes. Okay, so it's exactly the kind of thing you would expect. And okay, but how are we gonna do anything like this just using, dropping UA and using strongly compactness? So this uses an idea due to Wooden, a weak extender model for supercompactness. So he introduced these in his work on inner models for supercompact cardinals. Essentially, this is a weak extender model is an inner model. So a weak extender model for the supercompactness of kappa is an inner model M in which kappa is supercompact. The assumption here is that kappa is truly supercompact in V, and we've got this inner model M in which kappa is supercompact and it inherits this supercompactness of kappa in a natural way, V, or in the natural way from V, meaning that if you look at a supercompactness measure, there are supercompactness measures in V which themselves witness supercompactness in M. So their restrictions to M are in M, and they are supercompactness measures in M. So that's what a weak extender model for supercompactness is. And the reason Wooden introduce these is that he could show, sorry, I was supposed to call it N, that weak extender models for supercompactness for cardinal kappa are universal for large cardinals above kappa. So this suggested, or he argued from this, that sort of if you could solve the inner model problem, so build a canonical model for supercompacts, then you would actually build canonical models for large cardinal axioms beyond supercompacts. So that was the key argument he was making with these things. So one aspect of this universality for large cardinals is that every kappa complete ultrafilter, so n ultrafilter. So an ultrafilter on the Boolean algebra given by the n power set of some set belongs to n. Okay, so this is what we'll really need. And another thing that Wooden showed, basically to give an example of a weak extender model that's not just V. Of course, V itself is a weak extender model. Kappa is super compact. Kappa is super compact in V, and V inherits the super compactness of kappa in a natural way. Okay, but to show that this is not a totally trivial concept, I mean, you could think it might be because of this universality phenomenon. He also showed that if D is an ultrafilter on a cardinal less than kappa, and kappa is super compact, then the ultrapower of V by D is a weak extender model, or the supercompactness of kappa. So let's say a countably complete ultrafilter here, because otherwise it doesn't really make sense to ask whether alt VD is a weak extender model, because weak extender models are supposed to be inner models, and alt VD, if it's not countably complete, is not even well-founded. Okay, but if it is well-founded, then it is isomorphic to an inner model, so it makes sense to ask this question. Okay, and the point is now we have this silver diagram where we have an ultrafilter, which is supposed to be kappa gamma indecomposable, or aleph 1 gamma indecomposable. And we have this ultrafilter on omega and alt VD, and we would like to show that, you know, if there's a supercompact below gamma, then K, this factor embedding, is actually definable over alt VD. And so if there's a supercompact cardinal below gamma, then maybe the idea, which actually turns out to work, is that alt VD is some kind of weak extender model, even though it's ill-founded. Right, D is an ultrafilter on omega in the case of Silver's question. When we go back to cardinal preserving embeddings, we won't have to worry about ill-foundedness. But okay, we can generalize the theory of weak extender models to ill-founded models. So if there is a supercompact below gamma, alt VD is a generalized weak extender model. Okay, and the universality of alt VD for large cardinals above kappa just implies that K is definable over alt VD. Okay, so this gives us exactly what we want for this silver diagram. And in particular, it implies that if, well, so you can generalize this. So I wanted to state the theorem for strongly compacts for some reason. So generalize the theory of weak extender models to strongly compacts, and we also have to deal with ill-founded models, whatever. So if gamma is inaccessible, or even just regular, greater than the least strongly compact, then, and if gamma carries a uniform aleph 1 gamma indecomposable ultrafilter, then gamma is measurable. Okay, and actually we can get rid of this regular hypothesis even. So if gamma is any cardinal above the least strongly compact and it carries a uniform aleph-1 gamma indecomposable ultrafilter, then gamma is measurable or a limit of measurables. So in the second case, it will be a singular limit of measurables, actually of cofinality omega. Okay, and this singular case will be important to us because if you remember, with our cardinal preserving embedding, we're looking at an indecomposable ultrafilter on a singular cardinal, lambda plus kappa. Remember these U alphas that we derived from the cardinal preserving embedding that were lambda plus kappa indecomposable. Okay, so let's generalize this theorem in order to refute cardinal preserving embeddings from strongly compacts. So that was the idea of making this detour through Silver's ideas. So the generalized theorem says, so let me just say, what this tells us is, even though Sheard showed that Silver's question does not have a positive answer in ZFC alone, it does have a positive answer above the first strongly compact cardinal. So this tells us there's some sort of resemblance between the universe above a strongly compact cardinal and the canonical models, or the models of UA, sort of strange thing. Okay, so the generalized theorem says if lambda is a limit of strongly compact cardinals, and and gamma above lambda carries a lambda gamma indecomposable ultrafilter, uniform, it's important. Then either gamma is measurable or gamma is a limit of measurables. Okay, but lambda plus kappa, remember this is where we're looking for our indecomposable ultrafilter coming from the cardinal preserving embedding theta m. Lambda plus kappa is not measurable because it's singular, and it's not a limit of measurables because it's not even an aleph fixed point. So it's not measurable or a limit of measurables. So applying the contrapositive, this theorem, we obtain that lambda, our fixed point of the cardinal preserving embedding that we were looking at, we looked at an arbitrary fixed point of our cardinal preserving embedding above its critical. We got this uniform indecomposable ultrafilter on it. So we obtain that lambda is not a limit of strongly compact cardinals. So for any fixed point of J above the critical point, we can say that that fixed point is not a limit of strongly compact cardinals. Okay, but if there's a proper class of strongly compact cardinals, we would be able to find a proper class of limits of strongly compact cardinals that are fixed by J. This is, again, this fact that any elementary embedding of the universe of sets has a proper class of fixed points, an omega closed class of fixed points. So we can find an omega closed class of fixed points that are limits of strongly compact cardinals if there's strongly compact cardinals. So in other words, there isn't a proper class of strongly compact cardinals if there's a cardinal preserving embedding J from theta m. And okay, so take the contrapositive again, and we get the theorem. If there's a proper class of strongly compact cardinals, there's no cardinal preserving embedding from B to M. All right, so hopefully that's clear enough. We make this detour through the theory of indecomposable ultrafilters and through Wooden's idea of a weak extender model to obtain an analysis of indecomposable ultrafilters. Then we focus in on an indecomposable ultrafilter that's given to us by this cardinal preserving embedding, and show that such an indecomposable ultrafilter can't exist in close proximity to enough strong compactness. So I'm going to move on to section 2. But look, it's already been an hour, so maybe I will run out of my time. Okay, is everyone alive?
Yep. No, that was great. I think I basically followed the main idea really well.
Okay, great. So Vika is alive. No one else is showing signs of life, but that's okay.
I think I'm alive.
Okay. Who was that?
Andreas. Bloss.
Okay, Andreas Bloss is alive. That's okay. I'm
alive also.
I'm seeing lots of signs of life, so that's great. Let me continue to embeddings from M to V, unless anyone wants to ask me a question, in which case I would be so excited. Okay. So we're looking at these cardinal preserving embeddings from M to V, and these are really weird objects. And okay, so this lemma due to Caicedo is the reason I stayed away from cardinal preserving embeddings from M to V for so long. What it says is that if J from M to V is cardinal preserving, then J has no fixed points above its critical point. So all the fun we were having with this Omega Club class of fixed points of J from V to M is spoiled by these embeddings. They just can't fix anything at all. Okay, and so let me remind you the reason that that's weird for someone who's used to large cardinals that are not weird. Oh, sorry. The reason it's weird is normally what you would do to find a fixed point is, okay, you start at the critical point, you let kappa 1 be J of the critical point. Okay, this is how you find a closure point of any function on the ordinals, but okay, let's do it. So you keep iterating J, you iterate it omega many times, and you get this ordinal kappa omega. And then you say something like, well, kappa omega is the supremum of the kappa n's for n less than omega. So J of kappa omega should be equal to the supremum of the J of kappa n's for n less than omega. And that is equal to the supremum of the kappa n plus 1s. And that should be kappa omega again. Okay, but of course this won't work if the sequence of kappa n's is not in M. So that's the basic issue. And you know, it doesn't actually matter that we looked at the kappa n's. If M even saw that kappa omega had countable cofinality, it would have to fix kappa omega. Okay, but it doesn't. So kappa omega is kind of closed under J, but J has to be discontinuous at this ordinal of countable cofinality. So I'll show you why this is. I think that the proof I'll give is a little different from Caicedo's, and it involves Janssen cardinals, which I told you would be relevant in the situation of elementary embeddings from M to V. So recall that a cardinal lambda is Janssen if every structure in a finite vocabulary of cardinality lambda has a proper elementary substructure, cardinality lambda. So Janssen algebra, this is something that Janssen studied when he was doing universal algebra. It's a structure that has cardinality lambda that has no proper elementary substructures, cardinality lambda. And the existence of a cardinal's Janssen if there are no Janssen algebras. So equivalently, lambda is Janssen if for all or some or all sufficiently large alpha, let's say greater than lambda, there is an elementary J from M to V alpha, such that M is a transitive set, and J of lambda is equal to lambda, and critical point of J is less than. Okay, so Janssen cardinals are clearly related to this concept of an embedding from M into V. Well, you don't get embeddings from M into V like globally, because those kinds of things are kind of their second order objects. They can't ever be definable. But you do get embeddings from sets into levels of V. So to show you the relationship, well, first here's this theorem of Treiba and Wooden. I actually think I'm worried that I'm not giving the correct credit for the result. So Treiba and Wooden showed that if you have a regular Janssen cardinal, then every subset, every stationary subset of lambda reflects. And the theorem that I need from this, which maybe has an easier proof than the Treiba-Wooden argument, is that no successor of a regular cardinal or a successor of a regular cardinal is never Janssen. Successor of a regular cardinal is never Janssen. Try to speak English. So why is the successor of a regular cardinal never Janssen? Well, the successor of a regular cardinal always contains a non-reflecting stationary set, namely the set of all ordinals of cofinality, the predecessor, that can't reflect. Am I saying this right? Sure. Okay, so the proof of Caicedo's lemma is that we have, so suppose towards a contradiction that J is cardinal preserving from M to V, and J fixes this ordinal gamma above its critical point. Let's call it alpha, just so that you are sure that it's an ordinal, not necessarily a cardinal. Then J of alpha plus is equal to alpha plus, because alpha is the same computed in M or V. So because J of alpha is alpha, it's mapping the N double successor of alpha to the N double successor of J of alpha, which is alpha. So J of alpha plus is alpha plus. Okay, but then restricting J to some beta greater than alpha plus, we get an embedding I from N to Vj of beta with I of alpha plus equal to alpha plus, and critical point of I strictly less than alpha plus. So that would say that alpha plus is Janssen by this equivalent definition of the Janssen cardinal. But alpha plus is the successor of a regular cardinal. The successor of a regular cardinal is never Janssen. Okay, so we can prove Caicedo's lemma by analyzing Janssen. Okay, so these embeddings never have any fixed points. So they're really pathological. I mean, look, the point is they don't exist. That's what I'm going to show you today. But this is like a warning sign that the usual large cardinal theory doesn't really apply here. And also, another thing was I wanted to study the Ultrapower Axiom, show the Ultrapower Axiom implies there are no cardinal preserving embeddings, and the Ultrapower Axiom really doesn't help you here because you don't actually get any ultrafilters from J, just M ultrafilters. So that's a little annoying. But Sebastiano convinced me that we should look at this problem, and he was right. So sometimes when things are ridiculous, then you can prove that they don't exist. Okay. So what do we focus on to show, to get a contradiction, cardinal preserving embedding from M to V? The things you look at are, well, we don't have any fixed points, but we do have closure points of the embedding. Just cardinals lambda such that J image of lambda is contained in lambda. So we still have an omega club class of closure points of the embedding. We can restrict our attention to the ones that are strong limit cardinals, cofinality omega, because it's an omega club class, so we can, make them highly closed. Okay, so fix such a lambda above the critical point of J. Okay, and then the claim is that either lambda is a regular cardinal in M, or lambda plus is Janssen. So the idea here is, well, we had that the embedding is discontinuous at these cardinals like kappa omega, and that at least told us that kappa omega couldn't have countable cofinality in M, but actually turns out that kappa omega, well, either has to be regular or else you would get some very weird Janssenness. So this Janssenness here is strange, because it's a major open question whether you can ever have a successor cardinal be Janssen. Okay, so we're actually getting an example of a successor cardinal that's Janssen out of these things, so that's pretty weird. So how do you do this? The idea, well, okay, so I feel like I'm running out of time a little bit, so let me say just a little bit about it.
You can take your time. I'm fine with it. I think Ben is also.
Okay.
Take your time. I like following what you're saying. Maybe if you speed up, I will stop. So.
Okay. So what you do is we have this embedding from M to V. Here's our closure point lambda. And it's getting mapped way up because it has fixed points. And I want to factor this embedding. Okay, that's my one trick. So let D be the M ultrafilter derived from this embedding J using lambda itself. Okay, so we can take the ultrapower of M by this M ultrafilter D, and then we can find a factor embedding from alt MD into into V. Okay, so this is J sub D. All right, so this is the picture. So the id sub D will just be equal to lambda. So it's kind of like the situation for normal ultrafilters that I hope you're used to. And in the factor embedding, K is going to send lambda to itself. So it's just like when you derive an ultrafilter on a normal measure. The proofs are actually the same. Okay. So what happens here is we get that lambda plus is correctly computed by alt MD. So this is, it's very similar to what I was talking about before when I said that lambda plus kappa plus 1 is correctly computed in these ultra powers by coming from I2 embeddings. And I said this was part of the general theory of elementary embeddings, and I used some scare quotes, and I think I'm not going to give you the proof here either. I think I learned this kind of proof from CUNY paper he wrote about, I don't know, no, maybe it's from Kekris or something. Anyway, it's like you take an well ordering of lambda and you push it over to a well ordering of j of lambda in alt md, and then you restrict it down to lambda, and everything works well. So anyway, lambda plus is correctly computed by alt md because lambda plus was correctly computed by n. Okay. In particular, this means that this embedding sends lambda plus to itself. Okay, so it kind of looks like we've got that lambda plus is Janssen. But the one issue is that it's unclear whether the critical point of k is actually below lambda. So that's what you would need to know that lambda plus is actually Janssen, right? Then we have an embedding from this model alt md to v, and it fixes lambda plus, so it witnesses this alternative definition of the Janssen cardinal that I gave on the previous slide. But it's important that the critical point is below lambda plus, and that's not clear. What you would need for that to be clear is, well, one thing that you can use is if D concentrates on a small set, then you can show that the critical point is of the factor embedding is small, basically because the composition of K with JD is J, and that is discontinuous at so many cardinals. So K has to be doing something below lambda if D isn't doing that much. In the case where lambda is singular in M, it's pretty easy to show that D must concentrate on a small set. Okay, so we get if lambda was singular in M, then this K has a critical point below lambda, and therefore we get that lambda plus is Janssen. Otherwise, lambda is regular in M, so that proves our claim. Okay, so what we've done is we looked at all the closure points of this embedding J, and we show of cov omega. It's important that it's a strong limit here, and we've shown that they're either regular in M, so actually inaccessible cardinals in M, or else they have this very strange and interesting property that their successor is Janssen. Okay, so now let's talk about what we know in either of these cases. Sorry. So there's a theorem of Magador and Sinapova. This is kind of the general, a generalization of the fact that when you do a prick reinforcing, you create a square principle. Okay, so I'm going to show that either of these conclusions that we have from our claim leads to some kind of incompactness. Okay, so what square principle? Well, theorem of Magador and Sinapova says if lambda is singular of cov omega, and there is an inner model where lambda is regular and lambda plus is correctly computed, then this weak square principle, square lambda omega, holds. Okay, square lambda omega is just like the square principle, except you get countably many guesses. Okay, so it says that there's a sequence of sets C alpha for alpha less than lambda plus. Each C alpha is a countable set of closed cofinal subsets of alpha of order type less than lambda. And if you look at a limit point of one of the closed cofinal sets in C alpha, the restriction of a closed cofinal set to that limit point is in the corresponding C beta, where beta is the limit. Okay, so it's a version of the square principle, a slight weakening where you get countably many guesses. In any case, it's some kind of incompactness, and it won't be very important for you to know the precise definition. Okay, the other kind of incompactness we get from the other case, so where lambda is not regular in M, well, then we have that lambda was Janssen, And Sherlock proved that if lambda plus is Janssen, sorry, that's what we got, then the pseudo power of lambda is greater than lambda plus. Okay, so this is since we're in the situation where lambda is cov omega and a strong limit cardinal, this is the same as saying SCH fails at lambda. So we know from Solovey's theorem that SCH holds above a strongly compact cardinal, that a failure of SCH is a form of incompactness as well. Okay, so Sherlock showed, in fact, I think both these are due to Sherlock. So he showed that if lambda is singular, and either you have square lambda omega, or you have pp lambda is greater than lambda plus. These are two different theorems. I'm just putting them together for the sake of exposition. Then there is a good scale. At lambda. Okay, so what is a good scale at lambda? Again, it's not so important for your comprehension of the talk, but I will tell you the definition. So this good scale is going to be the thing that gives us a contradiction, but I won't really use it. So a scale at lambda, well, you have this cofinal omega sequence in lambda, since lambda is a cov omega cardinal. A scale in the product of those cardinals, I guess I should assume that they're regular, is a sequence of functions that is increasing and cofinal in the order of eventual domination. Okay, and a good scale is a scale with the following additional property. So for any new, sorry, I should have said the sequence has length lambda plus. So Sherlock proved, I mean, if you have SCH at lambda, it's trivial to see that there is such a thing. But Sherlock proved that there always is a scale. So you just have to pick the kappa n's correctly. A good scale has the following additional property. For any nu below lambda plus of uncountable cofinality, you can find a cofinal subset of nu such that, well, let's see, for some n less than omega, for all xi0 and xi1 in C with xi0 below xi1, and for all k greater than or equal to n, f sub xi0 of k is strictly less than f xi1 of k. So this is some kind of Ramsey-ish thing, I guess. You want to find, for any point in the scale of uncountable cofinality, you find a subset where instead of just being ordered by eventual domination, there's actually a single n for which after, they're all ordered by actual domination if you forget about the points below n. That's what a good scale is. So Sherlock showed that every singular cardinal of cofinality omega has a scale, but having a good scale is an incompactness property. So in what sense is that the case? Well, there's this theorem of Bulgarian and Magador from their paper on omega-1 strongly compact cardinals that says if kappa is omega-1 strongly compact, it doesn't really matter what that is. I mean, you can just think about strongly compact cardinals here. Then no singular cardinal lambda greater than kappa of countable cofinality carries a good scale. Okay, and their proof carries over exactly to our context. It just says if J from M to V is cardinal preserving, then no singular cardinal lambda greater than J of the critical point of J carries a good scale. Okay, so now we can prove, I guess, theorem 2. So this is the joint theorem with Sebastiano, that there are no cardinal preserving embeddings from M to V. The proof is just, let's see. We showed on the one hand, there is a proper class of singular cov-omega strong limit closure points of J are embedding V to M from M to V. On the other hand, all of these cardinals are supposed to carry a good scale. But that contradicts that there cannot be, by this lemma, a proper class of singular lambdas carrying good scales. Okay, so basically, if your large cardinal-ish axiom leads to an incompactness property, it's in a lot of trouble because it also leads to a compactness property, and those two things are in conflict. Okay, so that's the proof that there are no cardinal preserving embeddings from M to V. So I wanted to talk a little bit about some further results for cardinal preserving embeddings from V to M. So in the context where we're not assuming the existence of strongly compact cardinals, because it would still be interesting to know whether these can exist. It would be nice to rule them out in ZFC, but somehow this seems pretty hard. You know, I've thought about this problem much more than I ever thought about the problem for M to V, and actually Sebastiano and I also thought about this problem. So I don't know, it seems like a much more difficult problem. And okay, because I'm out of time, I won't tell you the further results for V to M, but thank you for attending. And yeah, so this should be the thanks slide.
Thanks very, very much, Gabe. That was great. I appreciated that you went slow enough for us to be able to follow. So, I mean, I think everyone must have gotten like at least the basic outline of how the proof went. So that was great. Questions for Gabe? I have sort of a philosophical question. So you said that these proposed embeddings were one way of trying to find a principle in ZFC that captures the strongness that otherwise the Kunin inconsistency embeddings given the ZF context. Are there any other proposed currently open possibilities in this direction?
Yeah, there are much, I think, more plausible proposals, although they're more complicated. So pretty recent theorem of Farmer Schlutzenberg shows that the following are equiconsistent. So one is ZFC plus I0. And so Wooden's axiom I0. So this is, there is an elementary embedding J from L of V lambda plus 1 to L of V lambda plus 1 point J as lambda. Okay, and then 2 is the hypothesis that CUNY ruled out, ZF plus, let's say, lambda DC plus J from V lambda plus 2 to V lambda plus 2. Okay, and 3, the same actually model has a J from V to M such that it's fully elementary, and V lambda plus 1 is contained. Even M to the V lambda plus 1 is contained in M. J of lambda is equal to lambda, point of J is equal to lambda. So omega huge cardinal. So this shows that these sort of I don't know, very large cardinal axioms proposed by Wooden actually are at the same level as these choiceless large cardinal axioms right at the beginning of the CUNY inconsistency theorem. So CUNY's proof shows that you cannot have ZFC with this, but here is a ZFC large cardinal axiom at exactly the right level. Now it's an open question whether there is a ZFC large cardinal axiom at the level of an elementary embedding from V lambda plus 3 to V lambda plus 3. I think that's one of the more interesting open questions in large cardinal theory. Although it's a little vague, there is a proposed one. So Wooden actually proposed a hierarchy of large cardinal axioms beyond I0 in his book or paper, very long paper, Suitable Extender Models 2. These are something called E0 alphas or something like this. Basically, the idea is that L of V lambda plus 1 is somehow like L of R, and you define a hierarchy of models that are analogous to the hierarchy of models over R in the context of determinacy, leading to the minimal model of ADR. And your axioms are asserting the existence of elementary embeddings from these models themselves. And the ADR model, the minimal model of ADR axiom looks like it could be exactly the level of a J from V lambda plus 3 to V lambda plus 3. And then there's this whole hierarchy of axioms that seems like conceivably they're axioms compatible with ZFC that could lead you to an inner model with a Reinhardt, with a J. The inner model satisfies that there's a J from P to P. So yeah, so there's a plausible picture now, I think, that could lead to an extension of the ZFC large cardinal hierarchy to meet the CF large cardinals.
I see. I mean, this is really interesting. I knew the first result, but not this Wooden's idea of that.
Mm-hmm.
Okay. Yeah. No, that's super interesting. Okay. Any other questions for Gabe? All right, Gabe, in this case, thanks very much again. And hopefully I might see you in New York in the summer. Let's see. And next week we have Mohammed Goshani. I have the abstract and the title already on the website. Looks like it's going to be another really interesting talk.